Can you imagine the next evolution in radiation medicine? At AKESIS, we did. Welcome to AKESIS. We're excited to share the next evolution in radiation medicine with you. Let's start here with the AKESIS Galaxy RTI, which recently received 510(k) clearance from the FDA. The AKESIS Galaxy RTI is the only SRS system with 360-degree rotational technology and real-time inline CBCT and kV-kV imaging. You can choose the best option for patient fixation and optical monitoring, as well as an industry-leading number of collimator sizes. Let's go in for a closer look. The AKESIS Galaxy platform represents the next generation of high-precision gamma systems for intracranial and head-based targets. With a more efficient imaging process, the enhanced ability to shape dose without reducing the dose rate, and a unique design to facilitate rapid source replacement, the AKESIS Galaxy series provides clinicians with a rotating gamma system with an impressive return on investment. Real-time imaging provides the ability to monitor and correct for patient positional changes throughout beam delivery, offering to improve the accuracy of mask-based treatments. Unlike fixed beam gamma systems, the AKESIS Galaxy has the imager and detector mounted on a rigid ring gantry at the same plane as the treatment beams. This means there is no couch shift required between imaging and treatment. Additionally, there is no regular QA required to validate separate imaging and treatment centers. Another significant benefit of the Galaxy's in-plane imaging system is the ability to perform real-time imaging. This enables both kV-kV matching for quick mid-treatment verification, as well as fully automated intrafractional skull tracking and corrections. During the past decade, the field of radiation oncology has been moving towards more rotational delivery options to leverage the inherent advantages of efficiency and the often enhanced ability to shape dose. The location of the imaging system at the treatment plane on the ring gantry supports full 360-degree cone beam CT acquisition, which provides better resolution than competitive systems, which acquire the cone beam CT in just 200 degrees. In addition, with the Galaxy's imaging system component centered near the treatment beam isocenter, the imaging beam geometry is improved significantly, reducing artifacts at the superior aspect of a cone beam CT. Let's see the Galaxy RTI in action. At the beginning of a fractionated radiosurgery treatment, a cone beam CT is acquired and registered to a planning dataset. Here you can see the inline imaging system acquiring the CBCT and subsequent couch offsets applied. Next, the collimator, located on the inner ring of the gantry, moves into position for treatment, and the treatment begins. While the treatment beam is on, we see the capture of a pair of orthogonal images taken at 0 and 90 degrees with subsequent couch corrections. This feature may not only help improve treatment accuracy, but it obviates the need for optical tracking and the potential associated treatment interruptions. If we look at the animation at the upper right of the screen, you can see the primary collimators located on the inner ring, rotating into the treatment position relative to the sources and secondary collimators, located under the black shape at the noon position on the ring gantry. As you can see, the inner ring containing the collimators rotates separately from the outer ring containing the sources. One advantage of this type of source arrangement when combined with rotational delivery is the ability to create user-defined partial arcs. When developing a treatment plan, the user can specify angles at which the beam is on or off for any part of a shot's rotation. This allows the planner to create beams that limit their intersection with adjacent critical structures, such as in the case of a trigeminal neuralgia or brain metastasis where the target is very close or abutting the brainstem. On the lower right, we can see a 3D animation of the non-coplanar beam geometry found in the Galaxy system. In this example, we show full 360-degree rotations at a gamma angle of 90 degrees. Next to that image, we see two partial arc beams used in a trigeminal neuralgia plan helping keep beams off the adjacent brainstem. The AKESIS Galaxy builds on well-proven isometric design principles that have been published in more than 2,000 peer-reviewed papers for gamma-based radiosurgery. However, the AKESIS Galaxy RTI offers the largest choice of automated collimator selections to build more complex composite shots, shrink-wrapping the dose distribution to the target. That's possible because of the unique source configuration. The AKESIS Galaxy systems contain 30 gamma sources. Rather than utilizing a distributed source arrangement, the Galaxy RTI places the sources in a compact carrier drawer. This unique characteristic provides a number of tangible benefits. Like static beam gamma systems, the sources are arranged in a non-coplanar and non-overlapping fashion with all beams focused on the target. This provides high focal dose uniformity, small focal spot penumbra, and fast dose fall-off away from the target. Another benefit of the compact source drawer design found in both the Galaxy RTX and RTI systems is the significantly streamlined source load and replacement process. In our process, sources are never handled individually. All gamma sources are loaded into their source drawer at the Nordian facility. They travel to the clinical site within a self-shielded source loading-unloading tool. In the case of a source reload, the spent source drawer is removed with 30 sources contained inside. Then a drawer containing the new sources is inserted into the machine. The process of inserting or removing a source drawer takes around 1 hour. Here you can see our source replacement process as compared to the industry standard. We estimate that the actual source replacement will take approximately 1 week, followed by the typical week of physics verification. By significantly reducing the amount of downtime associated with a source reload and supporting a quicker resumption of patient treatments, we help minimize the disruption to the clinic, allowing you to quickly return to your normal clinical operations. Rotating gamma systems are not new. In fact, they have a decades-long history of treating hundreds of thousands of patients, primarily in Asia. The AKESIS Galaxy series design follows US-based patents. While we share the basic concept of utilizing rotated gamma sources, our system represents a completely new design and workflow. These papers from the Red Journal in Medical Physics compare rotating gamma systems to the older model, electric gamma knife systems. The conclusion suggests that RGS systems are capable of achieving comparable targeting accuracy and dose distributions relative to their fixed beam counterparts. Similar to the original gamma knife systems, Galaxy systems employ isometric, non-coplanar, non-overlapping beams which converge on a common focal point with high targeting precision and conformality and fast dose fall-off away from the target. The AKESIS Galaxy RTI represents the next evolution in radiation medicine, improving treatment efficiency and precision while delivering a high return on investment. We invite you to learn more in our virtual showroom. Welcome to the evolution.
AKESIS has partnered with Prowess to provide treatment planning via the Prowess Panther SRS system. Now I'll go through a few treatment plans, including some of the most common stereotactic case types, to help demonstrate the clinical capabilities of the Galaxy system. First, we have your classic brain metastases. Here we see a solitary spherical 0.7 cm met, 1/2 cm from the brainstem. I planned this to 20 gray using a single 8mm shot. The conformality index was 1.04, the brainstem max dose was under 5 gray, and the treatment time was only 8 minutes. Next, we have a multi-met plan. In this case, there are 6 metastases ranging from 0.7 to 1.2 cm. I planned this to 14 gray using 11 shots and 2 collimator sizes. The brainstem maximum dose was under 4 gray, and the whole brain mean dose in B10 was only 0.8 gray and 4.3 cc's respectively. The treatment time for each target averaged around 5 minutes, with a total time of 30 minutes to treat all 6 lesions. Another standard SRS case, here we have a trigeminal neuralgia. While these cases are often planned without contours, using a single shot placed in the center of the nerve, in this case, we followed a more challenging protocol, where the goal is to treat the entire nerve to a minimum dose of 40 gray and a maximum dose of around 80 gray. The brainstem is only 1 millimeter from the proximal aspects of the target, making it quite challenging to spare while also meeting the target minimum dose requirement of 40 gray. For this plan, I utilized Galaxy's unique partial arc feature, easily setting the start and stop angles for a pair of shots, which greatly reduced the dose to the brainstem without any noticeable increase in treatment time. In the end, I was able to meet the minimum target dose of 40 gray, while the brainstem received only a 0.1 cc dose of 10 gray and a half cc dose of 3.5 gray. Finally, for larger, more irregularly shaped targets like this meningioma or an acoustic neuroma, manually placing multiple shots can present some challenges. In these cases, we can use the inverse planning module, standard feature in the Prowess TPS, to determine the ideal selection of shot placement, size, and weights. The image on the upper right shows the automatically placed shots, while the image on the lower right shows the dose distribution. In this case, other than prescribing to an isodose line to moderately rescale the dose, I did not need to change the inverse generated plan in any way to meet my clinical objectives. We've reached the end of this presentation. In closing, we believe the AKESIS Galaxy RTX and RTI represent the next generation of high-precision gamma systems for intracranial and head-based targets